This video is about Stokes Theorem, which is a 3D analog of Green's theorem. Specifically, it's the 3D analog of the tangential form of Green's theorem. The plan for this video is to review the tangential form of Green's theorem and what it means, and then extend it to 3 dimensions in Stokes theorem. And then we'll work a couple of example problems applying Stokes theorem and then interpreting it. Okay, so here's the tangential form of Green's theorem. It says that this line integral of f over c is equal to this double integral of the partial of n with respect to x minus the partial of m with respect to y under certain conditions. So if c is a piecewise smooth closed curve, and it's a boundary for a simply connected region R. Remember what that means. If R is simply connected, every simple closed curve in R contains only points that are in R. So we had a simply connected region with a piecewise smooth boundary. It's traversed counterclockwise. If for some reason it has to be traversed clockwise, you can always multiply these results by -1. And it's traversed exactly once. And F is a field in the xy plane with components m and n. And the component functions of our field have continuous first partial derivatives in an open region containing R. So I've created this little open region with this dotted line. So I'm just saying that these two component functions have continuous first partials inside that region, including R and on the boundary of R and just like a little bit outside that boundary. That's enough for us to get to state this result. Well, if all of that is true, then the line integral of f over this boundary is equal to the double integral of this function over the region R. So instead of evaluating this line integral, which requires parameterizing the curve C, writing f in terms of the parameter t, writing the unit tangent vector in terms of the parameter t, and then writing this as an equivalent integral in terms of our parameter and then evaluating it. Rather than doing all of that, we can just say, hey, if all of these conditions are satisfied, instead of doing that, we can do this. Now let's talk about what these two integrals mean, the integral on the left-hand side and the integral on the right-hand side. This is the line integral over c of f dotted with t hat times ds. Now, this can be interpreted a couple of different ways. If f is force, so I've got a force field in the xy plane. If I'm taking the dot product of the force with the unit tangent vector, what that would do is it would give me the component of the force that's parallel to the direction that we're going. And then it's multiplied by this tiny distance in the direction that we're going. So if I've got the component of force in the direction of motion times distance in the direction of motion, when I add all of that together, I get work. Now, if F represents the velocity field of a fluid, then we interpret this differently. But the mathematics is exactly the same. So if F is the velocity field of a fluid, let's say we're here. So this is our curve C, and here's our unit tangent vector at that location. If this is the velocity of the fluid at that location, if I'm finding the dot product of F with t hat, all that is it's finding the magnitude of the component of F in the direction of that unit tangent vector, but it's the signed magnitude. If F generally goes in the same direction as the curve, so that the projection of F onto t hat is in the same direction as t hat, that dot product will be positive. If F tends to go in the opposite direction, and when I say tends to, I mean if the projection of F that's parallel to t hat is not in the same direction as t hat, but goes the other way, then that dot product would be negative. So we take this measure of the amount of fluid that is still going in the direction of the curve, We count it as positive when it goes in the same direction that we're going. We count it as negative when it goes in the opposite direction. And then we multiply it by ds. And we add that up all the way around the curve, and we call that the circulation along C. So that is the tendency of that fluid to flow with C. If that is positive, we say net in general. There might be some locations where that dot product is positive, other locations where that dot product is negative. If this integral is positive, then the fluid tends to move around in the same direction as C, in that counterclockwise direction, because of our choice of orientation here. Now, if this dot product, or if this integral is negative, well, then the fluid has a tendency to go the other way. So if it's positive, in general, it tends to go in the counterclockwise direction. If this line integral is negative, in general, it tends to go in the opposite direction. So that is giving us circulation along C. So that's the tendency of the fluid to flow around C in this clockwise direction. Okay, so that's the left-hand side. And the right-hand side is this over here. And we showed earlier in the video on Green's theorem, or in one of the videos on Green's theorem, that this is actually the magnitude of the curl of F, where we treat F as a field, not in the plane, but as a field in space. So we've got this field with components M, N, and 0, because we're in the XY plane. Well, then when I take the curl of F, because it has no Z component, the curl of F is always perpendicular to the XY plane, so it's always parallel to K hat. If I take the curl and I dot it with K hat, that's just going to give me the magnitude, or the signed magnitude of the curl of F. Now, if that dot product is positive, all that means is this is a positive number. So the curl points up. And if the curl points up like this, that means that tendency to rotate is in that counterclockwise direction. Now, if this dot product is negative, that means the curl actually points down, it points into the page, and the curl goes in the direction of negative K hat. And then the rotation is not in the counterclockwise direction, but in the clockwise direction. So we take that, we multiply by a tiny area, and we do that for all of the little rectangles in the region R, for infinitely many rectangles in the limit. And that turns out to be the same as the circulation along C. So in other words, this is the curl, or the signed magnitude of the curl of F, which is giving us the tendency of that fluid to rotate about a point. We said informally that that's what the curl represents. It's really its magnitude. Its magnitude is proportional to the angular speed around that location. And even with this integral, we can say more specifically, well, this gives us the circulation along C. Well, this has got to be the circulation per unit area, because I'm taking circulation because this times area is giving us circulation. So I'm thinking of this as a circulation rate. I've got circulation per unit area at each location, then we're multiplying by area, and then we add them all together and we get circulation back. So on this side, what we have is a tendency to rotate, a measure of the tendency to rotate at every single point in the region R due to that field F. We're saying, does that field tend to rotate in the counterclockwise direction or in the opposite direction? If it does, the curl, or this dot product of the curl with K hat, in this case, is going to be non-zero. Take all of those and add those up. Well, if I take that tendency to rotate at every single point here in the region R, it turns out that that's exactly the same result we would get if we looked at that tendency to rotate around the outside, or that circulation of our field around C, or along C in the counterclockwise direction. Okay, so that's the tangential form of Green's theorem. Stokes theorem is basically the same thing, but it's in 3 dimensions. So here's Stokes' theorem. It says let S be an oriented surface with a unit normal vector n hat, and let it be bounded by a piecewise smooth, simple closed curve C. We remember what piecewise smooth means. It means it's smooth in pieces. It's okay if it has a few sharp corners, a finite number of sharp corners, that's fine. As long as it's smooth on each of those individual pieces, we're good. It has to be a simple closed curve C, so that curve can't cross itself. It has to be closed, so it has to start and end at the same place. And it has to have what's called a positive orientation. Now, what we mean by that is, if this is the normal vector n hat, and we're, let's say, standing above this, so we're in, like, maybe above the positive z-axis and we're looking down. So n hat is a vector, it's pointing out of the page, it looks like this, looks like that tip of my Sharpie that's pointed right at you. That's why it looks just like a little dot whenever we represent it that way. So n hat's going out of the page. If that curve C goes around it in the counterclockwise direction when n is pointed out of the page, so it's like n hat is where your thumb goes and your fingers are curling around in the counterclockwise direction, like you're using the right hand rule. Make sure you use your right hand, not your left hand, otherwise it'll be wrong. Then we say that C has a positive orientation. So we've got an oriented surface S with a unit normal n hat, and then relative to n hat, C has a positive orientation, so it's counterclockwise if we look at it from above. If that's true, and F is a field with components M, N, and P, and M, N, and P have continuous first partial derivatives on an open region that contains both the surface S and the boundary C, then this line integral over the boundary is equal to this surface integral over S. Now you can see the similarity between this and this. It's as if we took this region R, which we were formerly forcing to be in the XY plane, and we let it have a third dimension. So we've got this surface S here. What this is saying is the circulation of the fluid around the boundary C, and that's just how we interpret it if F is the velocity of some fluid. That circulation is equal to this dot product of the curl with n hat. So this dot product of the curl with n hat is multiplied by ds. So this is circulation per unit area, where ds is surface area. So I've got circulation per unit area times area, and that's going to give me circulation back. Okay. Now when I take the dot product of the curl with n hat, what that's giving me is it's giving me the signed magnitude of the projection of the curl onto n hat. So I'm saying, is there part of the curl that is parallel to n hat? Does it point in the same direction so that we're going in the counterclockwise direction relative to n hat? If it does, if that tendency at that location is counterclockwise relative to n hat, we're going to call that positive. If that tendency to rotate at that location is clockwise, this dot product will be negative. But we calculate this, we can think of this as the rotation of that field about n hat. So n hat is right there, and then we're looking at it from above. We're seeing if the circulation tends to be positive, so it's going counterclockwise, or negative, so it's going clockwise. And then we're adding all of that up. So we've got circulation here, and circulation here, and circulation here, and we've got circulation at all of these different points. Or we're computing the curl, or the signed magnitude of the curl relative, or in the direction of n hat. It's that part of the curl that goes in the same direction as our unit normal vector. We're adding all of that together. So now I've got this collective measure of the rotational tendency of our field while we're on the surface S. Turns out to be exactly the same thing as the circulation of the fluid around the boundary. So somehow what's happening on the boundary is completely determined by what happens inside. And what happens inside is determined by what happens on the boundary. I think that's pretty cool. Okay, now in practice, sometimes this integral is simpler to evaluate and sometimes this integral is simpler to evaluate. So we might have some desire to find the circulation of the fluid, but it's easier to compute this. So we would compute this instead of this. And sometimes we might have a desire to find the collective measure of that tendency to rotate all over the surface S. And rather than doing that, we might prefer to calculate the circulation around the boundary. So this theorem actually can go both ways. This equals this and this equals this. But sometimes we use this equality to find this by evaluating this, and sometimes we go the other way. Sometimes we use this to evaluate this. And we're going to tend to go in one direction. Rather than evaluating this line integral over the curve, we're going to tend to evaluate the surface integral instead. So let's do a couple of examples. Okay, so this says use Stokes theorem to evaluate the line integral over C of f dot t hat ds, where this is our field and C is the boundary of the first octant portion of the plane given by this equation. So the first thing we want to do is we want to sketch the plane. Well, not the whole plane, just the first octant portion of the plane. When x and y are both 0, we get z equals 12. When y and z are 0, we have 6x equals 12, so x must be 2. And if x and z are 0, we get 6y equals 12, so y must be 2. So this is our plane. So that is our surface, S. And the projection onto the xy plane, that's the region R, is that region down there. It crosses the y-axis at 2 and the x-axis at 2. It includes that back corner, the origin. So there's our region R. So we've got, that's S, that's R. And if you're wondering what the curve C is, the curve C is that boundary. So the unit normal might point out like straight out at us. We know that the normal vector of this plane is 6, 6, 1. We just read off the coefficients of the plane right here. So the normal points 6 units in the x direction, 6 units in the y direction, and just a little bit up in the z direction. It points out at us. Relative to that normal that's pointing out at us, and I'll put a little point like that to indicate that that normal is pointing out at you. And it has a component 6, 6, 1. Well, that's the normal vector. Yeah, that's the normal vector to the plane. Well, then relative to that, our curve C is this boundary. And we have to go around that boundary, in the counterclockwise direction. So we'll go this way, and then this way, and then this way, and then that way. All the way around C. Okay, so if this is C1, and that's C2, and that's C3, C is just the union of those. Okay, so we have sketched the first octant portion of S, and we've identified C. And we've oriented it positively relative to n hat. We also sketched the region R in the xy plane. So we have the projection of the surface onto the xy plane. And now we're here. So it says, use Stokes' theorem to evaluate this line integral, where this is our field and C is the boundary of this curve. Now, if Stokes' theorem applies, we're going to evaluate this line, or rather than evaluating this line integral, we'll evaluate a surface integral over the surface S. And that'll be really nice because it'll just be a single double integral as opposed to a line integral over C1 and a line integral over C2 and a line integral over C3 that we have to add together, find all three of those and add them. It's going to give us the same result as an equivalent surface integral over S. So that's the plan. We just need to check the conditions of Stokes' theorem before we use it. Okay, so the conditions of Stokes' theorem, let's get Stokes' theorem back out over here. So we have to have an oriented surface S, we do, with a unit normal n, bounded by a piecewise smooth, simple closed curve C. Definitely piecewise smooth, it's simple, it's closed, with a positive orientation. Yes, we made that counterclockwise relative to n. Okay, now our field has to have components whose first partial derivatives are continuous on an open region containing S and C. Well, the field is just some very simple polynomial functions in x, y, and z, so that's satisfied. Therefore, we can use the theorem. So I guess we needed to check those three things. We have an oriented surface S. With a piecewise smooth, simple, closed curve as its boundary. And of course, C needs to be oriented positively relative to n. Okay, and the last part, that's n hat. The last part is that the partials, the first partials of m, n, and p with respect to, well, all of them with respect to x, y, and z, all need to be continuous in an open region containing S and C. And since these are just polynomials, their first partials are continuous all the time. So we'll say m, n, and p have continuous first partial derivatives. And we'll just say since they are polynomials in x, y, and z. Okay. Since all of that is true, we can apply Stokes' theorem. So let's state the Stokes' theorem. And then we will set up and evaluate the surface integral. So the line integral over C, and that's a lowercase s, little arc length, is the same as the double integral over S of the curl of F dotted with n hat times ds. Excuse me. Okay, so what do we need to evaluate this? Well, it's a surface integral, so we need to, instead of evaluating the line or the surface integral over S, we evaluate an equivalent double integral, over the region R in the xy plane. So we will evaluate this instead. We'll have the double integral over R of the curl of F evaluated at X and Y, and whatever Z is in terms of X and Y. And then n hat, remember that's the gradient of G, and ds had that magnitude of the gradient of G in it, and the magnitude of the gradient of G was in the denominator of this unit normal vector. But those magnitudes reduced, and we just ended up with a dA over here. And this is where G is Z minus whatever Z is in terms of X and Y on our surface. Okay, so we need the curl, we need capital G, we need its gradient, we need to take a dot product, we need to describe R, we need to fill all of that in, and then we'll evaluate the double integral. So let's find the curl of F first. That's where I would start. And you don't have to write it that way, but I like to write it that way just to remind myself that the curl is a vector. It also helps here that I see it in a dot product, so it's pretty obvious that it has to be a vector. And the way you find it is you cross the del operator with the field F. So we'll have I hat, J hat, and K hat here. And in the second row of our determinant form of our cross product, we'll have the components of the del operator. And in the third row, we'll have the components of F. So that's X, Y, Z, Y, and Z. Okay. Now we'll cross out the row and column containing I hat, and then we'll evaluate these partials. The partial of Z with respect to Y is 0, and then we subtract the partial of Y with respect to Z, which is also 0. That's easy. And cross out the row and column containing J hat. We have the partial of Z with respect to X, which is 0, minus the partial of X, Y, Z with respect to Z. So that's a constant times Z, so we just get our constant back. And then cross out the row and column containing K hat. And then we take the partial of Y with respect to X, which is 0, and we subtract the partial of X, Y, Z with respect to Y. It's a constant times Y. The derivative of a constant times Y with respect to Y is that X, that constant, which is X times Z. So the curl ends up being 0 and XY times J hat, 0 times I hat plus XY times J hat minus XZ times K hat. And we're going to write this in terms of X and Y only. So this is the curl in terms of X, Y, and Z, but I need the curl in terms of X and Y only. In order to find the curl in terms of X and Y only, I have to find Z as a function of X and Y first. Compute or solve for Z. As a function of X and Y on your surface. Because remember, we're finding Z on the surface. So on the surface, we had 6x plus 6y plus z equals 12, and we can solve that for z. Z is 12 minus 6x minus 6, or not 16y, minus 6y. Okay, so now I know what z is in terms of x and y. It's this, so I can get the curl entirely in terms of x and y now. I need to write the curl entirely in terms of x and y. So you're just saying, remember, if you're on this surface given by this function, well, the curl in terms of x and y is xy times j hat minus x times all of that times k hat. So I'm just making a small substitution, replacing z with this. And you can distribute if you want to. You don't have to, though. Okay. And now we need g as a function of x and y, or excuse me, x, y, and z, so that we can compute its gradient. Basically, you need to get all of the terms on one side for this equation. That would be your g. Or you can solve for z like we did, and then have z minus g of xy, which is right here. Either one is fine. It'll be equivalent. You're going to get the same result. So we're going to solve for g and compute the gradient of capital G. So g is a function of x, y, and z, and it's z minus whatever z was in terms of x and y. So this is little g of xy. So I'm subtracting 12 minus 6x minus 6y, and if we simplify, we get this, just distributing the negative. Notice that's exactly the same thing that we would have here if we just subtracted the 12 from both sides. It's the same result, we just found it a slightly different way. So that's our capital G, and we want the gradient of capital G. It's a plane. Partial with respect to x is 6, partial with respect to y is 6, partial with respect to z is 1. 6, 6, 1, which is the normal vector of that plane, which we knew just from looking at this from our studies in that very first chapter. The normal vector can be found, the normal vector of a plane can be found by reading off the coefficients, 6, 6, 1. That's a normal vector. Same one. Okay. And this is what we needed. We need to take the curl and dot it with that gradient, and then set up the double integral over R. So we'll find the integrand next, and then we'll describe that region R right there. And we want this all in terms of x and y. So if your curl still has a z in it, you need to substitute. We already did though. So I've got 0 times I hat plus xy times j hat. And then I've got 6x squared plus 6xy minus 12x times k hat, dotted with 6, 6, 1. Remember how dot products work? You multiply component by component and add. So we'll get 0 plus this times this. And then we add this piece. Multiply, and we get 0, and then we add. Multiply and add. Multiply this by 1 and add. And so we get 6x squared, 6xy plus 6xy is 12xy. We're subtracting 12x. That's our integrand. Okay, great. Now let's look at it. We need bounds for R. Excuse me. So we find bounds for R. And we're right up here. You can let x go from a function to a function and let y go from a constant to a constant, or the other way around. Either way is fine. I'm just used to letting y go from a function to a function, so I'll do that. Y starts at 0, and then it ends at this line. That line has a slope of -2 over 2. It's like rise or fall over run. We go down 2 and over 2. So that is a slope of -1, and it crosses the y-axis at 2. So that's our y-intercept. So that equation of the line there is y equals 2 minus x. Meanwhile, x goes from 0 to 2. So x goes from a constant to a constant, and y goes from this line, which happens to be the x-axis, that's y equals 0, to this line, which is y equals 2 minus x. So we've got bounds. Then we just substitute our bounds and evaluate the integral. I don't know why people are intimidated by these theorems. It's a lot like U substitution. We're just substituting, doing a lot of algebra. It is tough though, because you have to remember all these operations from earlier in the course. You have to remember what everything means as well. We substitute the bounds and evaluate the double integral. That's the plan. Let's do it. That line integral over the boundary is equal to the double integral over R, and R can be described this way. X goes from 0 to 2, y goes from 0 to 2 minus x of our integrand. And that was the curl of f dotted with the gradient of capital G, all written in terms of x and y. So our integrand turned out to be this. And I'm just writing this here to remind you what we did to set this up. So everywhere we had a z, we replaced z with what z was while you're on the surface. Z was 12 minus 6x minus 6y because we were on that plane. We're on that first octant portion of the plane. We substituted and we got this. And then we just multiplied by dA. And this is, these are bounds for y, so we integrate with respect to y first and then x. Start on the inside and work your way out. The antiderivative of this with respect to y is just itself times y. That 12x is constant, so you bring it down. Antiderivative of y to the first with respect to y is y squared over 2. Add 1 to the exponent, divide by the new exponent. The antiderivative of 12x with respect to y, that's constant with respect to y, is that constant times y. Then you substitute in y equals 0 and y equals 2 minus x and subtract. So you have 6x squared times y, which is 2 minus x. And of course, 12 divided by 2 is 6. We have 6x times y squared. It's 2 minus x quantity squared. And then we have a negative 12x times y, which is 2 minus x. And then we evaluate all of this at y equals 0 and subtract, but when y equals 0, that's 0 plus 0 minus 0, so we just get 0. And that's that. This just needs to be simplified a little bit, so we could distribute that 6x squared here Distribute that negative 12x here. Maybe write that twice in FOIL. Just doing some algebra. If you write that twice in FOIL, you'll get 4 minus 4x plus x squared. Distribute the negative 12x. Now you want to distribute the 6x here. And let's see if there are any like terms we get to simplify. That would be nice, wouldn't it? Oh, I've got a 24x and a minus 24x. That's nice. And I've got a negative 6x cubed and a positive 6x cubed. That's nice. And then I have a 12x squared and 12x squared and minus 24x squared. What? Are you kidding me? It's the integral of 0. It's 0. Okay. It so happens to be 0. What's the area under this curve? We're going from 0 to 2, and the curve is just this. Well, there's no area, of course, so it's 0. All right. So what does this say? Let's say F is the velocity of some fluid. If there is a tendency of that fluid to go with the curve, there's also an equal tendency for that fluid to go against the curve. And when we take those dot products, the dot products that we have right here, and we add them all up as we go all the way around the curve, they just cancel out. That's what happens. So that this right here, which is that tendency to rotate about a point, when we take all of those tendencies and we multiply by the appropriate area and we add all of those together, we're going to have some tendencies to rotate in a clockwise direction, some tendency to rotate in a counterclockwise direction. We add all of those up and it turns out we get 0. So they all cancel here and they all cancel there. So that's what Stokes theorem means, and we evaluated it this way. You could prove to yourself that this is true by evaluating this as well, but that would require parameterizing C1, C2, and C3, writing F in terms of T, finding R prime, because that T hat ds, remember that's R prime of T dt if we simplify. Find R prime, dot it with F in terms of T, evaluate a line integral here and here and here. And if we've done everything correctly, you're going to get 0 over there because we got 0 over here. Okay, so that was our first example. Let's just do one more example. We'll call it a day. That'll be our last example in Calculus 3. All right, so we've got Stokes theorem again. We're asked to evaluate the line integral over C of f dotted with dr, where this is our field and C is the boundary of the surface S given by z equals 1 minus x squared minus y squared for z greater than or equal to 0. The first thing I would do is sketch the surface S and its boundary C. Well, I think we know, just from looking at it, we've been looking at a lot of different surfaces all semester. X and Y are both squared, they're both negative, z's raised to the first, so this is an elliptic paraboloid facing down. When X and Y are both 0, z is 1. It's not to scale, we get that. And then when z is 0, we're in the xy plane, and we actually have x squared plus y squared equals 1, so we'll have a circle of radius 1. I'm just going to draw my typical elliptic paraboloid. But remember that that's a circle of radius 1 down there. Now our surface is just this top part, and C is this curve down here. So if our normal vector is pointing out like this, then that counterclockwise orientation around the normal is that positive orientation. Now you have to remember that that is behind us. That's over in the part of the xy plane where x is negative. That's not sort of coming towards us. You have to remember that dimension that's there. So this is our surface. It looks sort of like this. And that's sort of in the background. Okay, so we've got S, and we have a piecewise smooth boundary C. Let's check all the conditions of Stokes' theorem. Do we have an oriented surface? We sure do. It has a top side and a bottom side. And with a unit normal, n hat, I chose the outward unit normal, or the upward unit normal, excuse me, not outward. It's not closed. It's the upward unit normal. And we have it bounded by a piecewise smooth, happens to be smooth. Simple, it doesn't cross itself, sure. Closed curve, yep, it starts and ends, or it just keeps going if we wanted to. But you could also say it starts and ends at the same spot. C, and it has a positive orientation. And positive orientation just means it's counterclockwise relative to n hat, and that is the way I drew it. Okay. Then if the field has component functions m, n, and p that have continuous first partial derivatives on an open region containing our surface S and C, then these two integrals are equal to each other. Yes, f has component functions that are all polynomials in x, y, and z. So we can apply Stokes' theorem. Said that incorrectly just now. So we check the conditions of Stokes' theorem and they're verified. I'm not going to write them down here. But sometimes you might be asked to verify them, so just make sure you go through your checklist and everything checks out. Okay. It checks out, so we can use Stokes' theorem. So let's state Stokes' theorem. So the line integral, oops, looks like an S. The line integral over C is equal to that surface integral of the curl of F dotted with n hat. And rather than evaluating that line integral over C, we're going to evaluate this curve on the other side. Actually, the line integral over C might be pretty simple. So I think maybe this time I'd like to verify Stokes' theorem. So I'll use Stokes' theorem, I'll calculate this and figure out what it is, and then I'll also do the other side and show that I get the same thing. Crossing my fingers, hoping I do everything correctly, so that actually works out. Okay, so we'll state Stokes' theorem, and now let's evaluate that surface integral on the right-hand side. Okay, so in order to evaluate a surface integral, we always, instead of integrating over the surface, we look at the projection of the surface onto the xy plane. That's the region R, and we can see that our region R is a circle of radius 1. Now, if you don't see that, the way I found that was I set z equal to 0 here. So you have 0 equals 1 minus x squared minus y squared. And then if you rearrange that, you get the boundary is x squared plus y squared equals 1. So that's right here. The projection R is that region inside. I've sketched it in red here, but it's this blue region down there. I'll make it blue over here too. Okay, so we evaluate this surface integral by looking at the projection of the surface onto the xy plane, and then we calculate the curl and n hat, but entirely in terms of x and y. So we need the curl of f in terms of x, y, and whatever z is in terms of x and y when we're on our surface. And n hat, that's the unit normal. That unit normal times ds can be simplified. It's just the gradient of capital G times dA, where capital G is z minus little g of x and y. So this is where little g of x and y is the equation of the surface, or one version of the equation of the surface, where z is equal to that. Okay, so this is the plan. That's what we're going to evaluate. So we need the curl in terms of x and y. We need capital G. We need its gradient. We need a dot product. We need to describe R in an appropriate coordinate system. Looks like we're probably going to switch to polar coordinates. And then we will evaluate this integral by plugging in the integrand and then integrating over R. Okay, so that's the plan. First thing we need is the curl. I always like to compute the curl first, just in case it happens to be the zero vector, and then we'll be done. And then when we do find the curl, if it has any z's in it, we want it in terms of x and y only. The curl of f is that del operator crossed with f. In the second row, we write the partials with respect to x, y, and z. Those are operators. In the third row, we write the components of f. So 4xz and y and 4xy. I cross out the row and column containing I hat, and then we take the partial with respect to y of 4x times y. Let's constant times y. The derivative of a constant times y is just the constant. And then we take the partial with respect to z of y. That's just constant, so we just get 0. Then we cross out the row and column containing j hat, and then we take the partial with respect to x of 4x times y again, so that's a constant times x. The derivative of a constant times x is just the constant. And then we subtract, so we crossed out that row and column. It's the partial with respect to z of 4x times z. Well, that's a constant times z. The derivative of a constant times z with respect to z is just the constant. And then we cross out the row and column containing k hat, evaluate the partial of y with respect to x, which is 0. And we evaluate the partial of this with respect to y, but there's no y's in it, so that's also 0. And we get this. Multiplying by that negative just changes the order of that. That would make that 4x minus 4y. Now, if there were any z's in this, I would have to replace z with whatever z is while we're on that surface. But there are no z's, so it's already in terms of x and y, so we're good there. Now we need the gradient of capital G. So we need to calculate G, and then we need to find its gradient. Now this was given to us. Our surface S is given by z equals 1 minus x squared minus y squared. So that's little g. We find capital G by subtracting this function from both sides. So we're setting this equal to 0 and making sure our z is positive. It's raised to the first. That just means the normal vector will be pointing up when we're done. So g of x, y, and z is z minus whatever z was in terms of x and y. And in terms of x and y, z was 1 minus x squared minus y squared. You want to distribute that negative. We get that. And now we want to compute the gradient of capital G. The partial of capital G with respect to x is 2x. Partial with respect to y is 2y. Partial with respect to z is 1. Okay. Not too bad at all. Now we just need a dot product of the curl with that gradient. That's our new integrand. Oops, I want black, not blue. So I've got 4x times I hat and 4x minus 4y times j hat, 0 times k hat. And we're doing this dot product. Remember how dot products work? You multiply and add, multiply and add. So we've got component times component, multiply. 4 times 2 is 8, x times x is x squared, and then we add. Multiply 4x minus 4y times 2y, and then add 0 times 1, and add. Distribute the 4y, or excuse me, the 2y. So we get 8xy minus 8y squared. That's our integrand. Okay. And we need double integral over r, and r is that circular region. We probably want to go to polar coordinates. So let's do it. So we'll set up and evaluate that surface integral. I think this one was probably much easier as the line integral. We'll see in a little bit. Okay, so we've got this line integral equals the double integral over r of our integrand, which we just found to be 8x squared plus 8xy minus 8y squared dA. And our region R is a circle. No, yeah, I think I still want to switch to polar. So I will write this in polar coordinates. R goes from 0 out to 1. Remember, you're thinking of circles radiating out from the origin. And theta is an angle. It goes from 0 to 2 pi. Now we need an integrand in terms of r and theta. And dA is r dr d theta. So I'm just going to write integrand for right now, and I'll fill that in. So let's find that integrand in terms of r and theta. Yeah, much easier with the line integral, I'm pretty sure. So I've got a factor of 8 that I can factor out of everything. And x is r cosine theta. We're squaring it. And then we're adding x times y. So that's r cosine theta times r sine theta. So that'll be r squared sine theta cosine theta. Minus 8 times y squared. Just distributing that 8 because there wasn't enough room on this line. Y is r sine theta, and we're squaring it. So I've got 8 times of r squared cosine squared plus r squared sine theta cosine theta minus 8 r squared sine squared theta. And I noticed right away that they all have an 8r squared in common, so I guess we could take out an 8r squared. We've got 8r squared, and we've got cosine squared plus sine theta cosine theta minus sine squared. Ooh, I see some trig identities there. I think I'm going to do that. Well, actually, I won't do it on a separate sheet of paper. I'll do it right here. Cosine squared minus sine squared. That turns out to be cosine of 2 theta. And sine of theta times cosine of theta is 1/2 of sine of 2 theta. Now, you don't have to use those trig identities. You can use other identities instead. If I didn't know what to do, I could use power reducing formulas for cosine squared and sine squared. Like, that's what sort of the rules would tell me to do. But as soon as I saw that cosine squared minus sine squared, I thought, oh yeah, there's that identity. Cosine squared minus sine squared is cosine of double the angle. And that's going to make my calculations just a little bit easier. Okay, so this is my integrand in terms of r and theta, but don't forget you have to multiply by that r from the dA. Almost done. So we've got the integral from 0 to 2 pi of the integral from 0 to 1 of 8r squared times an r, so that's 8r cubed, times cosine of 2 theta plus 1/2 sine of 2 theta. Integrate with respect to r first, and then theta. We can factor out that cosine of 2 theta plus 1/2 sine of 2 theta because that's all constant with respect to r. So we could factor out the 8 as well. Probably won't though. The integral from 0 to 1 of 8r cubed with respect to r. We find that, and then we evaluate the resulting integral with respect to theta. So I've got my constant, I'm bringing it down. Antiderivative of r cubed, we add 1 to the exponent and divide by the new exponent, evaluate from 0 to 1, and subtract. 4 goes into 8 twice. So I just end up with 2 times 1 to the 4th minus 0. So that's going to be 2 times 1, so we just get a 2 there. Let's distribute that 2. Integrate with respect to theta. Bring the 2 down. The antiderivative of cosine is 2 times, or 2 evaluated at the same angle. Since there's a number inside multiplying our theta, we divide by that number. Antiderivative of sine is negative cosine. Since I've got a coefficient there, I have to divide by that coefficient. These 2's reduce. Evaluate this from 0 to 2 pi. So we end up with sine of 4 pi minus 1/2 cosine of 4 pi minus sine of 0 minus 1/2 cosine of 0. Sine of 4 pi is 0, sine of 0 is 0, cosine of 4 pi is 1, cosine of 0 is 1. So we end up with negative 1/2 minus a negative 1/2. So we end up with 0 again. Wow, that was 0. Okay. A lot of these end up being 0 for some reason. So it turned out that this was 0, so that must mean that the line integral over that curve is also 0. And let's verify this by computing that. I want to show that it's 0 as well. So if I want the line integral of this field over C, I need a parameterization of C. And C is that curve in the xy plane, but we're thinking of it as existing in three-dimensional space. And that's a curve parameterizing that unit circle in the xy plane. So if I want a parametric representation of C, I've got to think of it as a parameterization of the unit circle in the xy plane, but it's existing in three-dimensional space. So if I want to go around that unit circle in that counterclockwise direction, which is what's necessary so that this curve is oriented positively relative to n, x should be cosine of t, y should be sine of t, and z should be 0. If we want the whole curve, t should go from 0 to 2 pi. Now, if I want the line integral of c over c of f dotted with dr, what that is, in practice, is f evaluated at x of t, y of t, and z of t, dotted with r prime of t, and then we integrate with respect to t. So we need the field in terms of t, we need r prime, we need a dot product, and then we'll integrate from 0 to 2 pi, because that's our a and that's our b. Okay, so I'm just going to write in this field in terms of t, and then we'll write in r prime in terms of t. R prime I'll do first, it's pretty easy. Derivative of cosine is negative sine. Derivative of sine is cosine. Derivative of 0 is 0. Now my field, the one I started with, was this. If z is 0, that component is 0. Then I just have a y and a 4 times xy over here. Y is sine of t, and then I've got 4 times x times y. So that's 4 times cosine of t times sine of t. Well, look what happens. When you take that dot product, you get 0 plus sine times cosine plus 0. And there's that trig identity again. That's 1/2 of sine of 2 times the angle. So we can anti-differentiate. Antiderivative of sine is negative cosine. Since there's a constant inside, we divide by the constant, evaluate from 0 to 2 pi. So we get negative 1/4 of cosine of 4t minus cosine of 0. So you get 1 minus 1, which is 0. So actually the line integral is much simpler in this case. But who knew? Okay, so we were able to use Stokes theorem to verify that. Let's briefly go over this and then we're done. I know you guys worked really hard. I'm proud of you. Multivariable calculus is tough. I hope you enjoyed it. I think it's really beautiful and interesting. Okay, so here's Stokes theorem. Got a surface S, it's oriented. So it's got a positive, or it's got a top side and a bottom side. And we want to orient it with a unit normal n hat. Usually we have it with oriented with the upward unit normal. And it's bounded by a piecewise smooth, simple closed curve C. It's positive orientation, which just means if you look at that surface from the top, so that n hat is sort of pointing up at you, curve C goes around it in a clockwise or counterclockwise fashion. So if I look at that from the top, if I go around this way, that's going to be counterclockwise. If all of that's true, and our field has components that have continuous first partial derivatives on an open region that contains that surface S and that curve C, then this line integral, which represents circulation of the fluid around that boundary, is equal to this. So we've got the dot product of the curl of F with n hat. Now remember what the curl is. It's a measure of that tendency of the field to rotate about a point. We see now that we're taking that tendency to rotate about a point and multiplying it by area, and we're getting circulation in an additive sense. So what this is giving us really is a circulation per unit area. Sometimes we call this the rotation of F about that unit normal. and we multiply it by a little surface area piece, and we add all of those together for all of the little pieces of the surface. That's the collective measure of this rotational tendency at every single location all over the surface S. Turns out that's exactly the same thing that you get when you calculate the circulation over the boundary. Now in practice, you can evaluate this or this. Typically in this class, we evaluate this one. Instead of evaluating the line integral over C, we evaluate this one instead, but we could just as easily go the other way. And the last problem, rather than evaluating this, I probably should have evaluated this one first, but we were asked to evaluate this using this, so we did. Now, a surface integral, remember how that works. You're never just going to integrate over the surface. You always have to look at the projection of the surface onto either the XY plane, the YZ plane, or the XZ plane. I have a tendency to project onto the XY plane because that's sort of easiest for us. Here's my example. Okay, so here we go. Here we are. If I want to evaluate this, what I need is the curl in terms of X, Y, and Z of XY, where Z of XY is Z as defined by your surface. And then instead of using this unit normal vector n hat, we calculate G, which is Z minus little g. We compute its gradient. That's entirely in terms of X and Y. And then we take a dot product. That's going to be our integrand. When you're done, you get a scalar function of X and Y. Excuse me. Then you need to describe the region R that you're integrating over and then just evaluate the integral. And so that's how we do that in practice. Congratulations, folks. I think you're finished with Calculus 3. At least you're finished with learning the new material. Now you just have to study for the final.